Please subscribe to support the channel. Look around you right now. You're surrounded by what appears to be solid matter. The chair beneath you, the walls around you, perhaps the device you're holding. Everything seems substantial, real, tangible. But what if I told you that all of this, everything you can see and touch, is almost entirely nothing? What if the reality we perceive as solid and full is actually an elaborate illusion masking an almost incomprehensible emptiness? This isn't science fiction or philosophical speculation. It's one of the most profound and counterintuitive truths about our universe, and understanding it will fundamentally change how you see reality itself. Let's start with something that will challenge everything your senses tell you about the world. If you could somehow remove all the empty space from every atom in every human body that has ever existed, if you could compress all of humanity down to just the actual physical matter without any of the space between particles, you could fit every single person who has ever lived into something roughly the size of a sugar cube. All 8 billion people alive today, plus the estimated 100 billion humans who have walked the earth throughout history, compressed into a space smaller than your fingernail. This isn't a thought experiment about some future technology. This is the actual ratio of matter to emptiness in the atoms that make up your body right now. You are, quite literally, more than 99.999999% empty space. The you that you think of as solid is actually a ghost of electromagnetic forces holding together particles separated by distances that, at their scale, are as vast as the distances between planets. But this atomic emptiness is just the beginning. When we zoom out from the subatomic realm to the cosmic scale, the emptiness doesn't diminish. It explodes into something far more extreme, far more absolute. The space between stars, between galaxies, between clusters of galaxies stretches into distances so vast that our Earth-evolved brains struggle to comprehend them. We live in a universe where matter is not the norm but the rare exception, where the overwhelming majority of existence is simply nothing. To understand our cosmos, to truly grasp the nature of reality, we must first confront this fundamental truth: the universe is, by almost any measure, spectacularly, monumentally empty. So how do we even begin to quantify this emptiness? How do astronomers and physicists measure what is, by definition, the absence of something? The answer lies in a concept called density, the amount of matter contained within a given volume of space. When scientists calculate the average density of the observable universe, they arrive at a number so small it almost defies comprehension. The average density of all the space we can see, encompassing billions of galaxies across billions of light years, is approximately 6 hydrogen atoms per cubic meter. 6 atoms. In a space the size of a large refrigerator. To put this in perspective, the air you're breathing right now contains roughly 25 billion trillion molecules per cubic meter. The universe, on average, is 40 trillion times less dense than the air in the room with you. What makes this even more remarkable is that this represents the best vacuum humanity has ever encountered. Our most sophisticated laboratories, our most advanced technology, cannot create a vacuum as perfect as the average emptiness of space. Even in the most carefully controlled vacuum chambers on Earth, where scientists have pumped out as much air as physically possible, the remaining density is still billions of times greater than the average density of the universe. We live on a planet that is, in cosmic terms, impossibly, almost obscenely dense with matter. We are inhabitants of an anomaly, a freakish concentration of atoms in a cosmos defined by their absence. This measurement of 6 hydrogen atoms per cubic meter represents what we call baryonic matter, the ordinary stuff made of protons, neutrons, and electrons that makes up everything we can see and touch. But even this infinitesimally small amount of matter isn't evenly distributed throughout space. It clumps together in galaxies, stars, and planets, leaving vast regions with far less than this already minimal average. There are enormous volumes of space that contain virtually nothing at all, regions where you might travel for hundreds of millions of light years and encounter fewer atoms than you could count on your fingers. To truly understand why the universe is so empty, we need to dive deep into the structure of matter itself, down to the level of atoms where this story of emptiness really begins. The ancient Greeks imagined atoms as tiny, indivisible spheres of solid matter, the fundamental building blocks from which everything else was constructed. They were spectacularly wrong. Atoms are not solid spheres. They're not solid at all. They are, in fact, almost entirely empty space with a few particles rattling around inside them at distances that, at the atomic scale, are astronomical. At the center of every atom sits the nucleus, a dense cluster of protons and neutrons bound together by the strong nuclear force. This nucleus contains almost all of an atom's mass, packed into an incredibly tiny space. How tiny? If you could scale up an atom so that it was the size of a large sports stadium, the nucleus would be about the size of a pea sitting at the center of the field. Everything else, all the space extending out to the walls of the stadium, would be occupied by electrons. But even calling it occupied is misleading because electrons don't exist as tiny particles orbiting the nucleus like planets around a sun. Instead, they exist in what we call probability clouds or orbitals, regions where the electron might be found if you were to measure its position. The electron doesn't have a definite location until it's observed. It exists in a quantum state of probability, smeared out across a relatively enormous volume of space. The numbers here are staggering. The nucleus of a hydrogen atom, the simplest atom consisting of just one proton and one electron, measures about 1 femtometer across. That's 1 quadrillionth of a meter, a number so small it's essentially meaningless to human intuition. The electron orbital, meanwhile, has a radius of about 50,000 femtometers. This means the electron occupies a volume that is approximately 125,000 billion times larger than the nucleus itself. If you think of the nucleus as containing all the actual matter, then more than 99.999999% of the atom is empty space. The solid objects you interact with every day are built from atoms that are almost entirely nothing. This raises an obvious question. If atoms are mostly empty space, why can't we pass through walls? Why does matter feel solid? Why can't your hand simply slip through the table it's resting on, given that both are overwhelmingly empty? The answer lies in forces, specifically the electromagnetic force, which is the reason matter maintains the illusion of solidity despite being mostly void. Understanding these forces takes us deeper into why the universe must be, by its very nature, predominantly empty. Every atom contains electrons, and electrons carry a negative electrical charge. When two atoms approach each other, their electron clouds begin to interact. Because electrons are negatively charged, and like charges repel, the electron clouds push against each other with tremendous force. This electromagnetic repulsion is what you feel when you touch a table or hold an object. You're not actually touching the object in the sense of your atoms making contact with its atoms. Instead, the electron clouds of the atoms in your hand are repelling the electron clouds of the atoms in the object, and your brain interprets this repulsive force as the sensation of touch, of solidity. It's an elaborate electromagnetic illusion. This same electromagnetic repulsion is what prevents matter from collapsing in on itself. Without it, the empty space within atoms would be meaningless because all the matter would simply crush together into an impossibly dense state. The electromagnetic force creates and maintains the emptiness within atoms by keeping electrons away from the nucleus and keeping different atoms separated from each other. It's a force of separation, a force that maintains distance and void. And it's extraordinarily powerful at the atomic scale, far stronger than gravity, which means that even though gravity is constantly trying to pull matter together, electromagnetic repulsion at the atomic level successfully resists this pull, preserving the emptiness. The strength of the electromagnetic force compared to gravity is difficult to overstate. If you take two protons and place them near each other, the electromagnetic repulsion between them is approximately 1 billion times stronger than the gravitational attraction between them. Gravity, despite being the force that holds planets in orbit and binds galaxies together, is actually the weakest of the four fundamental forces of nature by an enormous margin. This weakness is essential to understanding cosmic emptiness because it means that gravity, the only force that works at vast distances to pull matter together, is fighting a losing battle against the sheer scale of the universe. At the scale of atoms and molecules, gravity is so weak it's essentially irrelevant. Electromagnetic forces completely dominate. It's only when you accumulate enormous amounts of matter that gravity's effects become noticeable. A planet like Earth contains enough matter that gravity can overcome electromagnetic repulsion at the collective level, pulling all those atoms together into a sphere. But even then, the atoms themselves maintain their internal emptiness, and the distances between the atomic nuclei, while smaller than in a gas, are still vast at the atomic scale. When we zoom out to cosmic distances, gravity's weakness becomes even more apparent. Stars are separated by light years of empty space. Galaxies are separated by millions of light years. These distances are so vast that even though gravity is constantly working to pull matter together, it operates so slowly at these scales that other factors, particularly the expansion of space itself, easily overwhelm it. Gravity simply isn't strong enough to pull the universe into a dense, packed state. It can create local concentrations of matter like stars and galaxies, but between these concentrations, the emptiness prevails because gravity lacks the strength to bridge those enormous gaps. This brings us to one of the most revolutionary discoveries in the history of astronomy, a discovery that explained why the universe is not only empty but getting emptier with every passing moment. In the early 20th century, astronomers believed the universe was static, unchanging on the largest scales. Albert Einstein himself was so convinced of this that he added a mathematical term to his equations of general relativity specifically to keep the universe from collapsing under its own gravity. Then Edwin Hubble made an observation that would overturn this entire worldview. Hubble was studying the light from distant galaxies, and he noticed something strange. The light from these galaxies was shifted toward the red end of the spectrum, a phenomenon known as redshift. This redshift indicated that these galaxies were moving away from us, and the farther away a galaxy was, the faster it appeared to be receding. This wasn't because the galaxies were flying through space away from Earth. Instead, Hubble realized space itself was expanding. The fabric of the universe was stretching, carrying galaxies apart like dots on an inflating balloon. This expansion meant that the universe had been smaller in the past and was growing larger over time. And with this growth came increasing emptiness as matter became more and more spread out across an ever larger volume. The discovery of cosmic expansion fundamentally changed our understanding of why the universe is empty. It's not that matter was always spread out across vast distances. Rather, matter started out much more densely packed in the early universe, and expansion has been spreading it thinner and thinner over billions of years. Every cubic meter of space is constantly growing, creating more volume without creating more matter. The density of the universe is continuously decreasing as space expands. Where there were once 6 hydrogen atoms per cubic meter, expansion creates new space within that volume, reducing the average density. Given enough time, this expansion will make the universe even emptier than it already is. What makes this expansion even more remarkable, and more unsettling, is that it appears to be accelerating. Observations of distant supernovae in the late 1990s revealed that the universe's expansion isn't slowing down as astronomers expected it would due to gravity. Instead, it's speeding up. Something is pushing the universe apart with increasing force, overcoming gravity and driving everything farther and farther away from everything else. We call this mysterious pushing force dark energy, and it represents one of the most profound mysteries in modern physics. Dark energy makes up approximately 68% of the total energy content of the universe. Despite being the dominant component of the cosmos, we have no idea what it actually is. We know it exists because we can measure its effects, specifically the accelerating expansion of space. We know it has a negative pressure, which in the context of general relativity causes space to expand faster rather than slower. But its fundamental nature remains completely unknown. It could be a property of space itself, a kind of intrinsic energy that exists in every cubic meter of vacuum. It could be a new type of field permeating the universe. We simply don't know. What we do know is that dark energy is actively working to make the universe emptier. By accelerating expansion, it's increasing the distances between galaxies and clusters at an ever faster rate. In the far future, billions of years from now, dark energy will have pushed most galaxies so far apart that they'll no longer be visible to each other. Each galaxy or cluster will exist in a bubble of space surrounded by emptiness so vast that no light from other galaxies will ever reach it. The universe will become not just empty but isolated, with islands of matter separated by unbridgeable voids of nothingness. To understand how the universe became so empty in the first place, we need to go back to the very beginning, to the moment of the Big Bang and the first fraction of a second that followed. According to our current understanding, the universe began in an extremely hot, extremely dense state approximately 13.8 billion years ago. Everything that exists now, all the matter and energy in the observable universe, was compressed into a volume smaller than an atom. Then, in an instant, space began expanding at an incredible rate, and that expansion has continued ever since. But the standard Big Bang model alone doesn't fully explain the vast emptiness we observe. If space had simply expanded at a steady rate since the beginning, the universe should be much denser than it actually is. The solution to this puzzle came with the theory of cosmic inflation, proposed in the 1980s. According to this theory, during the first tiny fraction of a second after the Big Bang, specifically between about 10 to the negative 36th and 10 to the negative 32nd seconds, the universe underwent a period of exponentially rapid expansion. During this brief moment, space expanded by a factor of at least 10 to the 26th, and possibly much more. This inflationary expansion took whatever small region of space contained the seed of our observable universe and stretched it to enormous size in an almost incomprehensibly short time. Any matter or energy that existed was spread thin across this vastly expanded space. Inflation essentially took whatever initial conditions existed at the Big Bang and diluted them across a volume so large that matter became incredibly sparse. This is why the universe started out already quite empty, with matter spread across vast distances. Inflation set up the initial conditions for cosmic emptiness, and expansion has been making it emptier ever since. The inflation period also explains why the universe looks roughly the same in all directions. If we look at the cosmic microwave background radiation, the afterglow of the Big Bang that fills the universe, we see that it has almost exactly the same temperature in every direction, varying by only about 1 part in 100,000. This uniformity is puzzling because regions of the universe that are now on opposite sides of the sky were never in contact with each other if the universe expanded at a normal rate. They shouldn't have had time to reach the same temperature. But if the universe underwent inflation, these regions were in contact before inflation reached thermal equilibrium, and were then stretched apart faster than light could travel between them. Inflation explains the uniformity, but it also explains the emptiness. That initial contact and equilibrium happened in a tiny volume that was then blown up to cosmic size, spreading the matter incredibly thin. When we look out at the universe today with our most powerful telescopes, we don't see matter distributed uniformly through space. Instead, we see structure, a pattern that astronomers call the cosmic web. Galaxies are organized into clusters, and these clusters are arranged along vast filaments that stretch across hundreds of millions of light years. Between these filaments lie enormous empty regions called voids, areas that contain very few galaxies and almost no matter at all. This cosmic web structure is the result of tiny density variations in the early universe being amplified by gravity over billions of years. In the early universe, matter wasn't perfectly evenly distributed. There were regions that were slightly denser than average and regions that were slightly less dense. Gravity amplified these tiny variations. Denser regions attracted more matter, becoming even denser. Less dense regions lost matter to their denser neighbors, becoming even emptier. Over billions of years, this process sculpted matter into the web-like structure we observe today, with galaxies concentrated along filaments and vast voids in between. The voids represent regions where matter has been evacuated, pulled away by the gravity of the denser filaments and clusters. They are the emptiest places in the universe, regions where the cosmic average density of 6 atoms per cubic meter is wildly optimistic because these voids contain far less than that. The scale of these voids is almost impossible to comprehend. They can span hundreds of millions of light years across, containing perhaps only a handful of galaxies and volumes that could hold thousands, or even tens of thousands if matter were distributed at the cosmic average. Flying through one of these voids at the speed of light, which nothing with mass can actually do, would take hundreds of millions of years, and for most of that journey you would see almost nothing. No nearby galaxies, no stars except the few in your own galaxy if you started from one, just darkness and emptiness stretching in every direction for distances the human mind cannot truly grasp. One particular void stands out as an extreme example of cosmic emptiness, a region that has fascinated astronomers since its discovery. The Boötes Void, sometimes called the Great Void, is a roughly spherical region of space approximately 330 million light-years in diameter. To put that distance in perspective, it's about 3,000 times wider than our own Milky Way galaxy. In a region of space this large, if matter were distributed at the average cosmic density, you would expect to find approximately 2,000 galaxies. The Boötes Void contains only about 60 galaxies. It is spectacularly, almost impossibly empty. When the Boötes Void was first discovered in 1981 by astronomers conducting a survey of galaxy redshifts, some researchers wondered if it might actually be completely empty, containing no galaxies at all. Subsequent observations have found those 60 galaxies scattered throughout the void, but their presence only emphasizes the emptiness rather than diminishing it. 60 galaxies in a volume that large is effectively nothing. Most of the void is completely devoid of even these rare islands of matter. If you were located in a galaxy near the center of the Boötes Void and you looked up at the night sky, you would see almost no other galaxies. The nearest galaxies would be so distant that they might not even be visible to the naked eye. You would exist in an almost perfect isolation, surrounded by emptiness in every direction. The existence of the Boötes Void and other similar voids tells us something important about how structure formed in the universe. These aren't just random empty spaces. They're the result of matter flowing along gravitational gradients toward the denser filaments and clusters. The voids are the places left behind when matter evacuated toward regions of higher density. They represent the natural endpoint of gravitational structure formation in an expanding universe starting from small density perturbations. The voids are as much a part of the cosmic web as the filaments and clusters because you can have dense concentrations without creating empty regions in between. The structure and the emptiness are two sides of the same coin. We've been discussing emptiness at the cosmic scale, but let's bring it back to something more familiar, our own cosmic neighborhood. Even here, in what we consider a relatively dense region of space around our solar system, the emptiness is profound. Our solar system consists of the Sun and various planets, moons, asteroids, and comets bound by the Sun's gravity. Yet the vast majority of the solar system's volume is empty space. If you were to shrink the Sun down to the size of a basketball and place it in the center of a city, Earth would be about the size of a peppercorn located roughly 26 meters away. Jupiter would be roughly the size of a golf ball about 137 meters from the basketball sun. Neptune, the outermost planet, would be a marble about 800 meters away. These distances, even scaled down, reveal how empty our solar system is. The actual distances are staggering. Earth orbits the Sun at an average distance of about 150 million kilometers. Light, traveling at 300,000 kilometers per second, takes about 8 minutes to reach us from the Sun. Jupiter is 5 times farther away, Neptune 30 times farther. The space between these planets is not filled with anything substantial. There are occasional asteroids and comets, tiny specks of matter separated by enormous distances. There are particles of dust and atoms of gas, but the density is so low that this space is essentially a vacuum, far better than anything we can create in laboratories on Earth. Beyond the orbit of Neptune lies the Kuiper Belt, a region of icy objects and dwarf planets that extends to about 50 astronomical units from the Sun, where 1 astronomical unit is the Earth-Sun distance. Beyond that is the scattered disk, and farther still is the Oort cloud, a hypothetical spherical shell of icy objects that may extend out to about 100,000 astronomical units, or nearly 2 light-years from the Sun. This is still gravitationally bound to the Sun, still technically part of our solar system, yet the distances are so vast that it takes light 2 years to traverse from one side to the other. The density of objects in the Oort cloud is thought to be extraordinarily low, with enormous distances between individual comet nuclei. Our solar system, for all practical purposes, is almost entirely empty space with a few small objects scattered at immense distances from each other. But the emptiness of our solar system pales in comparison to the emptiness between stars. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system, located approximately 4.24 light-years away. That's about 40 trillion kilometers or 270,000 astronomical units. To put this in perspective with a useful analogy, if the Sun were the size of a grapefruit sitting in New York City, the nearest star would be another grapefruit sitting in Los Angeles, about 4,000 kilometers away. Everything in between would be empty. No other stars, no planets from other solar systems, just the occasional grain of dust representing an atom or two in the interstellar medium. At these scales, even our most advanced spacecraft become almost useless. Voyager 1, humanity's most distant artificial object, launched in 1977 and has been traveling outward ever since at about 17 kilometers per second relative to the Sun. After more than 45 years of travel, it has covered less than 1/600th of the distance to Proxima Centauri. At its current speed, it would take about 75,000 years to reach the nearest star, if it were headed in that direction, which it isn't. The distances between stars are so vast that interstellar travel, at least with current or foreseeable propulsion technology, remains firmly in the realm of science fiction. The space between stars is called the interstellar medium, and while we call it empty, it does contain a sparse distribution of matter. The average density in the interstellar medium near our Sun is about 1 atom per cubic centimeter, which is about 1 million atoms per cubic meter. This is far denser than the cosmic average of 6 atoms per cubic meter, but it's still an almost perfect vacuum by Earth standards. For comparison, the air you're breathing contains about 25 billion trillion atoms per cubic meter, which means the interstellar medium is about 25 billion trillion times less dense than air. This extremely sparse gas, consisting mostly of hydrogen and helium with traces of heavier elements, is the thickest concentration of matter you'll find in interstellar space. This brings us to a counterintuitive aspect of emptiness. Even when we talk about empty space, even when we describe the vacuum of space between stars or between galaxies, that vacuum isn't truly empty at the deepest level. Quantum mechanics reveals that what we call empty space is actually seething with activity at scales far too small to observe directly. The quantum vacuum is filled with what physicists call virtual particles, particle-antiparticle pairs that pop into existence and annihilate each other in timescales so short they seem to violate the principle of energy conservation. But these quantum fluctuations don't actually violate any physical laws. They're permitted by the Heisenberg uncertainty principle, which allows energy to be temporarily borrowed from the vacuum as long as it's paid back quickly enough. These virtual particles are not just a theoretical curiosity. They have real, measurable effects. The Casimir effect, predicted in 1948 and experimentally confirmed, shows that two metal plates placed very close together in a vacuum will experience an attractive force because the quantum vacuum between them contains fewer virtual particle modes than the vacuum outside. This proves that the quantum vacuum has structure and energy, even though it contains no actual particles. In some sense, the vacuum is not empty but full of potential, a roiling sea of quantum activity that averages out to nothing but never actually reaches nothing at any given instant. However, it's crucial not to overstate the significance of quantum vacuum fluctuations when discussing cosmic emptiness. While these fluctuations are real and important for quantum physics, their energy density is still incredibly small. The virtual particles exist for such brief moments, and in such limited ways that they don't fundamentally change the fact that space is empty of actual matter. The quantum vacuum doesn't contain objects you could point to or mass you could weigh in any conventional sense. It remains, for all practical purposes related to cosmic structure and the distribution of matter, genuinely empty. The quantum fizz at the smallest scales doesn't fill the void between galaxies or make the universe any less empty at the scales we've been discussing. Understanding the quantum vacuum does, however, connect to one of the mysteries we mentioned earlier, dark energy. One hypothesis for what dark energy might be is that it represents the energy of the quantum vacuum, a baseline energy density that exists everywhere in space. If this were true, it would mean that empty space itself has energy, and this energy causes the accelerated expansion we observe. The mathematical problem with this idea is that when physicists calculate what the energy density of the quantum vacuum should be, they get a number that is about 120 orders of magnitude larger than the observed dark energy density. This is perhaps the worst prediction in the history of physics. Something is clearly wrong with either our understanding of the quantum vacuum, our understanding of dark energy, or both. The nature of empty space at the quantum level remains one of the deepest mysteries in physics. Let's now look at what the universe actually contains, breaking down its composition to understand just how little of it consists of ordinary matter. When cosmologists tally up everything in the universe and calculate what contributes to its total mass energy content, they find a surprising distribution. Ordinary matter, the stuff made of atoms that makes up everything we can see, touch, or detect directly, accounts for only about 5% of the universe. This includes all the stars in all the galaxies, all the planets, all the gas and dust in interstellar and intergalactic space, everything you've ever seen or could ever see with any telescope. All of it together is just 5% of what's out there. Another 27% consists of dark matter, a mysterious form of matter that doesn't interact with electromagnetic radiation, which means it doesn't emit, absorb, or reflect light. We know dark matter exists because we can observe its gravitational effects. Galaxies rotate in ways that can't be explained by the gravity of their visible matter alone. Galaxy clusters bend light from more distant objects in ways that require far more mass than we can see. The motion of galaxies within clusters indicates they're being held together by much more gravity than their visible matter can provide. All these observations point to the existence of matter we cannot detect directly, matter that doesn't interact with light, or ordinary matter except through gravity. We call it dark matter because it's invisible, but that's about all we know. Its fundamental nature, what particles it's made of, remains unknown despite decades of experimental searches. The remaining 68% of the universe is dark energy, the mysterious force driving accelerated expansion that we discussed earlier. When you add these numbers up, you get a startling picture. 95% of the universe consists of things we don't understand and can't directly observe. And even the 5% that is ordinary matter is spread so thinly across the cosmos that it might as well not be there for most purposes. The universe is not only mostly empty of matter, but most of what does exist is invisible and mysterious to us. Even within that tiny 5% of ordinary matter, most of it exists in extremely diffuse forms. The majority of ordinary matter is in the form of gas in intergalactic space. Hydrogen and helium spread so thinly that cubic meters of this space contain only a handful of atoms. A smaller fraction is locked up in stars, which are themselves tiny dense points separated by vast empty spaces. An even smaller fraction exists as planets, asteroids, comets, and other dense objects. When you're standing on Earth, surrounded by solid matter, you're experiencing an environment that is wildly unrepresentative of the universe at large. You're in one of the rarest states of matter concentration that exists anywhere in the cosmos. This extreme emptiness of the universe turns out to be not just an interesting fact but a necessary condition for our existence. If the universe were significantly denser, if matter were packed more closely together, the environment would be hostile to life as we know it. Consider what would happen if stars were much closer together. In our galaxy, stars are separated by light years, which means close stellar encounters are extremely rare. A star passing close enough to our solar system to disrupt planetary orbits might happen once every few billion years, if that. This stability is crucial for life. Earth has been orbiting the Sun in roughly the same way for over 4 billion years, providing the stable conditions necessary for life to emerge and evolve. If stars were packed 10 times more densely, encounters would be thousands of times more frequent. Planetary orbits would be regularly disrupted. A planet might orbit one star for millions of years, then have its orbit altered by a passing star, sending it into a different trajectory or ejecting it from the system entirely. Complex life requires billions of years of stable conditions to evolve. In a denser universe with frequent stellar encounters, such stability might never exist. Planets would be flung around like pinballs, and the long-term stability necessary for life would be impossible. A denser universe would also mean a more intense radiation environment. Stars produce radiation, and if stars were much closer together, the background radiation level would be much higher. Life on Earth is protected from most cosmic radiation by our atmosphere and magnetic field, but these protections have limits. If the radiation environment were orders of magnitude more intense, life might never have gained a foothold on Earth, or anywhere else. The mutations caused by radiation would be too severe, too constant, for evolution to produce increasingly complex organisms. The emptiness between stars provides a radiation-friendly distance, a safe zone where planets can orbit without being sterilized by their neighbors' outputs. At larger scales, the emptiness between galaxies serves a similar protective function. If galaxies were packed closer together, galactic collisions would be more common. Our Milky Way galaxy is on a collision course with the Andromeda galaxy, but this collision won't happen for another 4 billion years. In a denser universe, such collisions might happen much more frequently. During galactic collisions, the gas clouds within galaxies are compressed, triggering massive bursts of star formation. These bursts produce many large, short-lived stars that end their lives as supernovae, flooding the galaxy with deadly radiation. A universe with more frequent galactic collisions would be a universe where radiation sterilization events are more common, making the long-term survival of life less likely. The emptiness also matters for the formation of structures themselves. In the early universe, matter needed to clump together under gravity to form stars and galaxies. This process requires a delicate balance. If the universe were much denser, matter would have clumped together too efficiently, forming massive black holes rather than stars. If it were much less dense, matter might never have clumped together enough to form stars at all. The actual density of our universe appears to be in a narrow range that allows stars, galaxies, and the structures necessary for life to form. The emptiness is not just a backdrop but an essential parameter for cosmic structure formation. This leads us to what philosophers and physicists call the anthropic principle, the observation that the universe must be compatible with the existence of observers, or else there would be no one to observe it. The anthropic principle comes in different forms, from weak to strong versions, but the basic idea is straightforward. We shouldn't be surprised to find ourselves in a universe with properties that allow observers to exist because we couldn't exist in a universe with different properties. The emptiness of the universe can be understood partly through this lens. We observe an empty universe because only an empty universe, with the specific density and expansion rate our universe has, allows for stable stars, stable planetary systems, and the billions of years of stable conditions necessary for complex life and consciousness to emerge. Some physicists take this idea further, suggesting that our universe might be one of many, perhaps infinitely many, universes with different properties, a concept called the multiverse. In this framework, most universes might be too dense or too empty, expanding too quickly or collapsing too rapidly, having physical constants that don't allow for complex chemistry or stable structures. We find ourselves in one of the rare universes where the conditions are just right because those are the only universes where observers can exist to ask why the conditions are just right. The emptiness of our universe might not be a cosmic accident but a selection effect. We exist in an empty universe because empty universes are the only kind that can support life. Whether or not you find the anthropic principle or multiverse theories compelling, they highlight an important point. The emptiness of the universe is intimately connected to our existence. We are not separate from cosmic emptiness but products of it. The vast distances between stars gave our Sun and solar system a safe, stable environment. The vast distances between galaxies kept our Milky Way relatively undisturbed during the billions of years life was evolving on Earth. The emptiness within atoms allowed complex molecules to form and react. The emptiness we observe isn't a bug in the universe's design, it's a feature that made our existence possible. Looking forward in time, the universe's emptiness will only increase. We've discussed how cosmic expansion is accelerating due to dark energy, and this acceleration has profound implications for the far future. Currently, we live in an era where galaxies are still relatively close together. We can see billions of galaxies with our telescopes. Our own galaxy is part of what's called the local group, a small cluster containing about 50 galaxies bound together by gravity. The Andromeda Galaxy, our nearest large neighbor, is clearly visible in the night sky from Earth with the naked eye under dark conditions. But dark energy is pushing most galaxies away from us at ever-increasing speeds. As expansion accelerates, galaxies that are not gravitationally bound to our local group will recede faster and faster. Eventually, these galaxies will be receding so quickly that their light will no longer be able to reach us. They won't disappear suddenly but will fade as their light becomes more and more redshifted, until finally they cross what's called the cosmic event horizon, a distance beyond which no signal can ever reach us because space is expanding too fast. Once a galaxy crosses this horizon, it's gone from our view forever. Over the next 100 billion years or so, most of the galaxies we can currently see will cross this horizon and disappear from view. The universe, from the perspective of observers in our local group, will appear to contain only the galaxies in our immediate gravitational neighborhood. The rest of the universe will have vanished beyond the cosmic horizon. The night sky will become darker, emptier, containing only the merged remnant of the Milky Way and Andromeda galaxies, along with the few dozen smaller galaxies in our local group. Any astronomers that exist in this distant future will look out at the universe and see almost nothing beyond their own galaxy. They'll have no evidence of cosmic expansion, no distant galaxies to observe, no cosmic microwave background that has been redshifted into invisibility. Their view of the universe will be profoundly limited compared to ours. This future isolation will continue for trillions of years as stars continue to form from the remaining gas in galaxies, burn through their fuel, and die. Eventually, all the gas will be locked up in stellar remnants like white dwarfs, neutron stars, and black holes, or ejected from galaxies entirely. Star formation will cease. The last stars will flicker out, leaving galaxies as graveyards of dead stellar remnants orbiting in darkness. The universe will enter what cosmologists call the degenerate era, a time when the only sources of light are the occasional flashes from white dwarfs colliding or matter falling into black holes. But even this won't be the end of the emptiness. Given enough time, even the structures that currently exist will dissolve. Galaxies will slowly evaporate as stellar remnants occasionally interact gravitationally, flinging each other out into intergalactic space. The timescale for this process is almost unimaginable, something like 10 to the 19th years, 10 billion years, about 1 billion times longer than the current age of the universe. Over these vast epochs, even gravitationally bound structures will come apart, spreading matter ever thinner across the expanding void. The universe will become even emptier than it is now, with isolated stellar remnants drifting through darkness separated by distances that dwarf the current distances between galaxies. Eventually, even black holes will evaporate through a process called Hawking radiation, predicted by Stephen Hawking in the 1970s. Black holes emit a thermal radiation due to quantum effects near their event horizons, and this radiation carries away energy, and therefore mass. For stellar mass black holes, this evaporation takes something like 10 to the 67 years. For supermassive black holes at the centers of galaxies, it takes even longer, around 10 to the 100 years. But given enough time, even these will evaporate, leaving behind only photons and fundamental particles spreading apart in an ever-expanding, ever-emptying universe. The final state, sometimes called the Big Freeze or heat death, is a universe that has expanded to such enormous size and low density that it's essentially empty. The temperature approaches absolute zero. No structures exist. No stars shine. Nothing happens. The universe becomes a cold, dark, nearly empty void stretching across distances so vast that the distances between galaxies today would seem microscopic by comparison. If the current universe is empty, this future universe will be empty beyond any meaningful comparison. It represents the ultimate endpoint of the emptiness we observe today, taken to its logical extreme across timescales that make geological time look like an eye blink. This far future scenario emphasizes something crucial about cosmic expansion. It limits not just where matter is but what we can observe. Even today, in what we might consider the universe's youth, there are limits to what we can see. The observable universe has an edge not because space ends there but because light from beyond that distance hasn't had time to reach us yet. The universe is approximately 13.8 billion years old, which means light has had 13.8 billion years to travel toward us. Anything farther away than the distance light could travel in that time is beyond our observable horizon. But there's a complication. The universe has been expanding during that time, so the edge of the observable universe is not 13.8 billion light-years away but about 46.5 billion light-years away. This is because the space between us and distant objects has been stretching while the light was traveling toward us. An object that emitted light 13.8 billion years ago was much closer then, but space has expanded since then, carrying that object farther away. By the time the light reaches us, the object is now 46.5 billion light-years distant. This expanding light travel distance defines the size of the observable universe, a sphere with radius 46.5 billion light-years centered on Earth. Beyond this horizon lies more universe, possibly infinitely more, but we can never see it. The light from objects beyond this distance simply hasn't had time to reach us yet, and due to accelerating expansion, light from sufficiently distant objects will never reach us. These regions are causally disconnected from us, existing in a part of space that we can never observe, communicate with, or influence. The universe may be vastly, even infinitely, larger than the portion we can see, filled with countless galaxies and structures we'll never know exist. From our perspective, these regions might as well not exist because we can never receive any information from them. They represent the ultimate form of emptiness, not empty of matter necessarily, but empty of any possible connection to our observable reality. This observational horizon has interesting implications for how we understand the universe's emptiness. When we measure the density of the universe and find it to be 6 atoms per cubic meter, we're measuring only the observable universe. The true universe could be much larger, even infinite, and we have no way of knowing whether the density we measure in our observable region is representative of the universe as a whole. It's possible that other regions of the universe, far beyond our horizon, have very different densities. Perhaps there are regions much denser than ours, regions where stars are closer together and galaxies are packed more tightly. Or perhaps there are regions even emptier than the voids we observe, vast expanses of space with essentially no matter at all. The expansion of the universe and the finite speed of light create a kind of cosmic isolation. Each point in space has its own observable universe, its own horizon beyond which it cannot see. For observers in distant galaxies, their observable universe would be centered on their location, not ours. They would see a different set of galaxies, with some overlap with what we see but also many galaxies we cannot observe. The total universe, if we could somehow view it from outside, would contain far more structure and matter than any single observer could see. But from any point within the universe, including ours, vast portions of existence remain forever hidden, contributing to a kind of observational emptiness even if those regions are filled with matter. To put the universe's emptiness in perspective, let's compare the densities of different environments across a wide range of scales. This will help us appreciate just how extreme cosmic emptiness really is compared to the environments we're familiar with. Starting from the densest environments we know and moving toward the emptiest gives us a sense of the staggering range of densities that exist in nature. At the dense extreme, the center of an atomic nucleus has a density of approximately 10 to the 17 kilograms per cubic meter. This is matter packed so tightly that a sugar cube of nuclear density material would weigh about 100 million tons. Neutron stars, the collapsed cores of massive stars, have densities approaching this nuclear density. They're essentially giant atomic nuclei about 20 kilometers across. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. This represents the densest stable matter we know of in the universe. Moving down in density, we come to the metals and other solid materials we encounter in daily life. Iron has a density of about 7,900 kilograms per cubic meter. Water, the liquid that makes up most of Earth's oceans and our bodies, has a density of 1,000 kilograms per cubic meter. Earth's atmosphere at sea level has a density of about 1.2 kilograms per cubic meter, about 800 times less dense than water but still extraordinarily dense by cosmic standards. Now let's jump to space. The best vacuum we can create in laboratories on Earth achieves pressures of about 10 to the negative 17 atmospheres, corresponding to a density of roughly 10 to the negative 14 kilograms per cubic meter. This is incredibly empty by Earth standards, but it's still far denser than most of the universe. The interstellar medium near our Sun, which we described earlier as containing about 1 million atoms per cubic meter, has a density of about 10 to the negative 21 kilograms per cubic meter. That's about 10 million times less dense than the best laboratory vacuum. The average density of the universe, those 6 hydrogen atoms per cubic meter, corresponds to about 10 to the negative 26 kilograms per cubic meter. This is 100,000 times less dense than the interstellar medium near Earth and 100 trillion times less dense than the best vacuum we can create in laboratories. But we can go even emptier. The intergalactic medium, the space between galaxies, has a density of roughly 10 to the negative 28 to 10 to the negative 29 kilograms per cubic meter, about 100 times less dense than the cosmic average. Finally, the cosmic voids we discussed, like the Boötes Void, have densities that may be as low as 10 to the negative 30 kilograms per cubic meter or less. These are the emptiest places we know of, regions where you might travel for millions of light years and encounter only a handful of atoms. The density range from the center of a neutron star to the heart of a cosmic void spans about 47 orders of magnitude, a range of 10 trillion 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 trillion. The universe contains both the densest and emptiest environments imaginable, but the vast majority of its volume exists at the empty end of this spectrum. Living as we do on a planet with a solid surface, surrounded by an atmosphere, near a star, in a galaxy, we experience an environment that is at the extremely dense end of the cosmic spectrum. Our perspective is fundamentally skewed by our location. We evolved in and are adapted to an environment that is wildly unrepresentative of the universe at large. It's like living your entire life in the dense heart of a city and trying to understand the geography of a continent that is mostly wilderness, desert, and ocean. The city is real, but it's a tiny exception to the general rule. This brings us to perhaps the most profound aspect of cosmic emptiness, what it means philosophically for our understanding of existence and our place in the universe. For most of human history, people believed Earth was the center of everything. The sky was a dome overhead with the heavens beyond. Stars were lights affixed to celestial spheres. Everything in existence revolved around us, literally. Then Copernicus showed that Earth orbits the Sun rather than the reverse. We were demoted from the center of creation to one planet among others. Subsequent discoveries continued this process of cosmic demotion. The Sun is one ordinary star among hundreds of billions in our galaxy. Our galaxy is one ordinary galaxy among hundreds of billions in the observable universe. We occupy no special place, no privileged position. The discovery of cosmic emptiness takes this demotion even further. Not only are we not at the center of the universe, not only are we located on an ordinary planet around an ordinary star in an ordinary galaxy, but we live in a type of environment, a dense concentration of matter, that represents a tiny exception to the general nature of the cosmos. The universe is defined by emptiness, not by matter. Void, not substance, is the default state. We exist in a rare pocket of density, a statistical fluctuation in an overwhelmingly empty cosmos. Our entire galaxy, everything we can see, all the stars and planets and gas clouds that make up the Milky Way, could be removed from the universe and the overall picture would barely change. The universe would still be, for all practical purposes, entirely empty. This realization can provoke different reactions. For some, it emphasizes human insignificance. We are specks on a speck orbiting a speck in a sea of nothingness. Our entire existence, our history, our civilizations, everything we've ever cared about occurs in a tiny region of densified matter surrounded by incomprehensible emptiness. When we consider the vast voids between galaxies, regions where nothing happens and nothing exists for distances that light takes hundreds of millions of years to cross, our brief lives on this small planet seem almost meaningless. But there's another perspective, equally valid. The fact that we exist at all in such a universe is remarkable. The universe didn't have to be capable of producing observers. The physical constants could have been different, the initial conditions could have been different, and no stars would have formed, no planets, no life, no consciousness. Yet here we are, products of atoms forged in stars, living on a planet orbiting a stable star in a relatively quiet region of a galaxy, able to look out at the universe and comprehend its vastness and emptiness. We are the universe's way of knowing itself, rare concentrations of matter organized in such a way that they can observe, think, and wonder about their origins. The emptiness makes our existence more special, not less. In a universe packed densely with matter, life might be common and unremarkable. In a universe as empty as ours, where the conditions necessary for life are so specific and so rare, the fact that those conditions arose at all is extraordinary. We are improbable arrangements of atoms in an improbable pocket of density in an inconceivably vast and empty cosmos. Our rarity doesn't diminish our value but emphasizes it. We are witnesses to existence itself, conscious beings who can contemplate the void and our place within it. The emptiness also emphasizes the importance of connection. In a universe where everything is separated by such vast distances, where isolation is the norm and proximity is the exception, the connections that do exist become precious. The fact that atoms came together to form stars, that stars produced heavier elements, that those elements formed planets, that on at least one of those planets molecules organized themselves into life, and that life eventually evolved the capacity for consciousness and understanding, represents a chain of connections spanning billions of years and countless events. Each connection was improbable. Each step could have failed. Yet the chain held, and here we are. Human civilization represents another level of connection. Across our planet, billions of people are connected by culture, language, trade, information, and increasingly, digital networks. These connections, like the physical connections of atoms in our bodies and planets in our solar system, exist in defiance of the universe's tendency toward separation and entropy. We maintain our connections, our structures, our order, by constantly expending energy. Life itself is a rebellion against the cosmic trend toward disorder and emptiness. We are local reversals of entropy, temporary islands of increasing complexity in a universe that overall is becoming more disordered and more empty. Looking up at a dark night sky far from city lights, you can see perhaps a few thousand stars with your naked eye. Each of those stars is a sun like ours, possibly with its own planets, possibly with its own forms of life looking back toward us. The darkness between those stars, the black background of the night sky, is not empty space in our galaxy but the space too far away to show individual stars. Most of what you see is actually darkness, the visual representation of emptiness. That darkness is most of what exists. The points of light are the exceptions, rare concentrations of matter doing something interesting, burning hydrogen into helium and heavier elements, shining across the void. With a telescope, you can see farther, revealing not just stars in our galaxy but other galaxies beyond, each containing billions of stars. The Hubble Space Telescope's deep field images, where the telescope stared at a tiny patch of apparently empty sky for days, revealed thousands of galaxies in that single patch. Everywhere we look, when we look deeply enough, we find more galaxies stretching away into the distance. The universe is full of galaxies, which seems to contradict the claim that it's empty. But those galaxies are separated by distances so vast that even light takes millions or billions of years to cross between them. The volume of space between galaxies is so much larger than the volume occupied by galaxies that calling the universe empty remains accurate despite the abundance of galaxies. If you could somehow travel to the middle of intergalactic space, halfway between our galaxy and Andromeda, about 1.3 million light-years from both, and you looked around, you would see the Milky Way as a faint smudge of light in one direction and Andromeda as a faint smudge in another direction. Everything else would be darkness. No nearby stars, no planets, no gas clouds, just empty space stretching in every direction. The density of matter around you would be far below the cosmic average. You would experience emptiness in its purest form, and you could travel for 1,000,000 years at the speed of light before reaching any significant concentration of matter. This is the universe we inhabit. This is the cosmos that produced us. It's a universe where matter is the exception and emptiness is the rule, where distances are so vast that light, the fastest thing that exists, takes billions of years to cross them, where the space within atoms mirrors the space between galaxies in its emptiness. It's a universe that started in an extremely dense state and has been expanding and thinning for nearly 14 billion years, and will continue expanding and thinning forever, becoming ever more empty as time goes on. The question we started with was why the universe is mostly empty. We've explored many answers: the emptiness within atoms maintained by electromagnetic repulsion, the weakness of gravity compared to other forces, the expansion of space stretching everything apart, dark energy accelerating that expansion, the initial conditions set by cosmic inflation spreading matter thin from the very beginning, the structure formation process that concentrated matter in galaxies and left vast voids between them. All these factors contribute to the emptiness we observe. But perhaps the deepest answer is that the universe is mostly empty because that's the only way a universe capable of producing observers could be. A denser universe would collapse on itself, or form only black holes. A universe expanding faster would never form galaxies or stars. The precise balance of density, expansion rate, and fundamental forces that we observe appears to be necessary for structure formation, for stars to shine long enough for life to evolve, for planets to orbit stably for billions of years. The emptiness is not a bug but a feature, not a failure of creation but a necessary condition for our existence. We are children of the void, born in rare pockets of density within an overwhelmingly empty cosmos, and the void made us possible. When you look at the night sky and contemplate the darkness between the stars, you're seeing the fundamental nature of reality. The lights are beautiful and fascinating, but the darkness is most of what exists. The emptiness is not nothing, it's the canvas on which the rare and precious concentrations of matter paint their stories. Your body, mostly empty space at the atomic level, is organized emptiness shaped by electromagnetic forces. Your planet orbits through the emptiness surrounding the sun. Your star shines into the emptiness between stars. Your galaxy moves through the emptiness between galaxies. And beyond the edge of the observable universe, more emptiness stretches out farther than we can ever see, possibly forever. This is the universe, a vast, expanding emptiness containing rare islands of matter that temporarily resist the cosmic tide toward maximum entropy and isolation. We live on one of those islands, and from here we can observe the great empty ocean surrounding us and wonder at its scale, its age, its future, and our place within it. The universe is mostly empty because that's what the universe is, fundamentally at its core. The emptiness is not the absence of something, it's the presence of everything. It's the space through which light travels, the distance across which gravity operates, the medium in which time unfolds. The void is not death but possibility, not absence but potential. In recognizing the universe's emptiness, we recognize our own improbable fortune to exist at all in such a place. We are the universe awakening to itself, rare patterns of matter complex enough to observe the void and comprehend it. Every star you see, every galaxy beyond, every atom in your body represents a triumph over the cosmic default of separation and disorder. The universe is mostly empty, but in that emptiness, it made room for us to exist, to think, to wonder, and ultimately to understand that the void itself is what makes the light possible. Without the darkness between the stars, there would be no stars to shine. Without the emptiness, there would be nothing and no one to appreciate the rare concentrations of existence that do occur. The universe is mostly empty. This is perhaps the most fundamental fact about the cosmos. It's a truth that challenges our intuitions, contradicts our immediate sensory experience, and reveals the nature of reality at scales both smaller than atoms and larger than galaxies. From the quantum vacuum to the cosmic voids, from the distances within atoms to the distances between galaxy clusters, from the present moment to the heat-death trillions of years hence, emptiness defines existence. And yet, in this overwhelming emptiness, here we are, alive and aware, products of the rare density, observers of the abundant void, witnesses to the greatest story ever told, the story of a universe that is almost entirely nothing, and the miraculous something that briefly exists within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.